Okay, so welcome everybody. Thank you for being here. Today is also a special day, time for a very small celebration because this session marks exactly 1 year from the very first Glow meeting. So we are super happy and grateful to all the people that follow Glow from the very first day. And thanks to all the new faces that are joining today. So there's still people coming. Okay. Today we're back to the original format. So we're going to have two talks. The first from Celia Rubio-Madrigal. Thanks to both the speakers to having accepted the invitation. And Celia will tell us how to um, to merge community aware and feature similarity in graph rewiring. While for the second speaker, we are going to have Lawrence Kummer that is going to present how to attack GNN with bit flips, in particular targeting the injectivity of genes. So how to make the Weisfeld lemma going indifferent to graph differences, let's say. So two very interesting talks. I think if I haven't forgotten anything, we can start with Celia.
Awesome. Thank you so much, Katerina.
You're welcome. Thank you for joining.
Yeah, and everyone else also for the invitation and yeah, for organizing this and for everyone for showing up and listening to this talk. So, as Katerina said, I'm going to speak about graph rewiring and concretely some places or some kinds of graphs where this might fail or this some kind of tasks. And the interplay between the task and the structure of the graph is going to be very important in this talk. And when I say graph rewiring, I usually mean a pre-processing step where we add or delete edges before sending it to together with the task to a GNN or another graph-aware model. And well, this talk or this work is done in collaboration with my colleague Adarsh Jamadandi, who is also around here, hopefully, and my supervisor Rebekka at my institute, CISPA. And the work that I'm going to talk about mostly is called GNNs getting comfy. So I hope that everybody gets comfy for this talk. um, yeah, but first of all, I'm going to give a little bit of a graph learning introduction so that we are all on the same base and that, well, like my assumptions for this talk are clear. So we're working with attributed graphs, which are a set of nodes which are interrelated with a set of edges that we are given. And these nodes have some kind of data attached to them, which are its features. And that's why they are attributed. So I am not considering that the edges have features in this talk, although they could be just like given to the nodes instead. So if there's some kind of features on the edges, then you can give it to like the adjacent nodes. But yeah, I'm just considering that the nodes are the ones that have some kind of features in them, and we can have directed or undirected graphs. That's not a problem. So in terms of the task or how the task or the test data that we consider, and there's mainly two kinds of ways in which we can consider test data for this kind of for node prediction specifically. So, well, I've not said it, but I'm going to mostly work with node predictions so that each node has a different label, and we won't want to mainly classify or do a classification on top of this prediction, this label. And the two ways in which we can do this is the inductive way, in which the test nodes are not known beforehand, and so you also don't know where they will attach to the original graph that you have trained on. You have a full graph, and then some extra nodes will be attached. And on the other hand, we have the transductive setting where all the nodes are there and all the edges are there, but you just don't know what labels the test nodes will have. And in this talk, I'm going to focus more on the transductive setting just because I'm working with edges and how to delete or add them. And so it's very useful to have all of them at the beginning so that I can do something in a pre-processing step. That doesn't mean that the insights don't transfer to the inductive setting, but obviously I'm just going to assume that all of the edges are already there and we know them. Now, how do graph neural networks work? So in normal tabular data, the standard neural network will learn a function on just the inputs. However, in the graph neural network, as a lot of you might know, we learn node representations layer by layer, and each layer has an update on some kind of aggregated information. This aggregated information comes from each of the neighbors that give information to each of the nodes. And so we get, we aggregate information from the neighborhoods, and that means that the edges are used in order to compute the kind of node embeddings or node representations that the model learns. Therefore, the matrix or the adjacency matrix, the set of edges, are really important in this computation. So we say that the adjacency matrix has a computational role in graph neural networks. As shown here, maybe this is more clear with a little bit of an example. We learn how to aggregate or update aggregations depending on which model we are using. And as I've said before, this is very important, but the edges are used for this computation. And the way that the nodes communicate to each other is very important in how the information mixes with each other. So I've already talked about this, but then the graph, one of the main insights is that the graph is used as a computation for the model, but it is also given as data. The data meaning which nodes are connected to each other. So there's some kind of two roles going on with graph neural networks, and graph rewiring explores mainly or usually the computational one, while sometimes ignoring a little bit the data part. And our work tries to bring back the data into this kind of discussion. Now, exactly what do I mean by these computational challenges? Not all input graphs can propagate the information that easily. So for instance, we can think of bottlenecks, as the first picture shows here. So we can think that the information that is from one of these communities into the other community will not flow properly. And so there are some graphs that may not be optimal or may not work as a computational structure, even if the task is given like this, right? There are a lot of tasks that could have bottlenecks, and this is completely normal in terms of the data, but perhaps not in terms of mixing information or using it for computational purposes. So how to solve computational purposes, the computational challenges? We can add or delete edges in order to solve these issues, and we have to be very careful on which ones we are deleting or which ones we are adding, of course, because the graph still carries some valuable relational structure, or so we have to take that into account. Now, the specific computational challenge that I will be talking about here is oversquashing, which is like very well known, although sometimes very differently defined. So the way that you can define this is still a matter of like, it's still in the literature or it's still being discussed. And so I'm going to focus here on a specific kind of oversquashing and a specific way of defining it. And hopefully this also, translates to other kinds of oversquashings. And we can think of structural bottlenecks that are the problem, where an exponential amount of information has to go through a node in order to be communicated to other nodes, right? And especially as the layers or as the number of hops or neighborhoods increase. And one way that we can find these bottlenecks that I've been talking about, there's many ways. So for instance, the curvature of the edges. So we can define different settings of curvature. Another way is by checking sensitivity while like mixing the information. This also takes into account maybe the features, but here I'm not using these definitions. Instead, I'm using the spectral gap. And the spectral gap is exclusively a property of the adjacency matrix, so of the edges of the graph. And it is basically the leading eigenvalue of the normalized Laplacian, which is the operator that we use in order to mix the information. And when this spectral gap is low, we assume, or it means, or we define that there is some kind of bottlenecks in the network. And this is a global measurement that speaks about the whole graph. But one thing that we can do is to try to add edges that increase this property. And the edges that maximize this spectral gap are the ones that we would choose to fix these bottlenecks, or the picture below, where we are adding edges across these communities in this specific graph. And in this way, we have solved, or we have mitigated these structural bottlenecks. This is a common way. And in another, well, this is a bit of an advertising for another work that preceded the one that I'm talking about in this talk. But in this previous work that we had, we focused on seeing what the advantages were of removing edges instead of adding edges, which was the more intuitive way of rewiring, especially to improve information flow or connectivity. So in this work, we proved that removing edges is also possible in order to increase connectivity, which is not obvious at all, but it is true based on the Bayes paradox or complex network science. And this has some benefits. So for instance, we look at the effect of oversmoothing, and we see that by removing edges, we can mitigate oversmoothing as well as increasing the spectral gap. And so we are kind of slowing down both things at the same time. And therefore, they are not necessarily a trade-off, depending on how you define them, of course. Now, after looking at this kind of removing edges or this way of improving connectivity, we went on to study whether improving connectivity is always a good thing. So is it always necessary to improve this connectivity, or are there tasks, are there graphs where this is not necessary, or moreover, is this even detrimental? And we will see that this is the case. So when should the spectral gap increase? Is the spectral gap maximization always beneficial? And now I come to the main paper that I'm talking about in this talk, and it was published in iClear this year. So yeah. And what we want to bring here is, as I've said before in the introduction, some cases in which increasing the spectral gap is detrimental to the task. And for that, we have to really take into account how the task is defined on top of this adjacency matrix, on top of these edges and nodes. And when I say task in this talk, I'm going to be a little bit generic. I'm not going to say exclusively the labels or exclusively the features. I'm going to say what is on top of this graph structure. So what is used for the task. So we're going to look at how this scale of communities or community structure is aligned with the task. And so for that, we are looking at a specific graph model, which is the SBM. It's a very commonly used model to see the effect of communities on some tasks. And we have an example here of a two-block SBM or stochastic block model. And when I refer to communities, you can see here that the green nodes are a specific community and the gray nodes are another specific community. And because we have attributed graphs, as I've said also before, we have to define some kind of features and well, the labels too, but we have to define some features. So I'm going to take the community label that is given by the stochastic block model, or the partition of the graph. And so I'm going to do like a Gaussian feature per community. And the label, well, in this case, will be the same as the community label. So if it is the same as the community label, that means that the task is a kind of community detection problem, where we are trying to detect what community this node is in. However, if the community labels and the actual labels of the task that we are trying to deduce or predict are not the same, then we will say that it has a different alignment. So it is a different alignment between the graph and the task. This is all needed in order to understand the setup of what we're talking about, and specifically the kinds of graphs that might fail with graph rewiring. And so the main theorem or the main insight with this work is that spectral gap maximization reduces the strength of the community structure in the SBMs. And spectral gap minimization, that is choosing the edges to add or delete that minimize the spectral gap, increases the community structure. So the underlying community structure that is in the graph will be increased or decreased in minimization or maximization, respectively. So what does this mean exactly for the task. This means that if the communities are somehow informative, so if the community structure of the graph has something to say for the task, that means that reducing the strength of the community structure is a bad thing. It's detrimental. And so maximizing the spectral gap is detrimental and should be used very sparingly. Now, we prove this for the case of the for the SBMs, which is again a very used way of taking into account communities into a graph, and or studying the effect of the community structure for a specific kind of graph. And the first theorem is exactly what I've said before, which is that a less pronounced community structure corresponds to a higher spectral gap. Now, maybe perhaps obviously, but reducing the community structure harms performance. And this is the case when the labels of the task are aligned with the labels of the SBM, that is, the labels of the community structure. And as I've said before, that means that it is a kind of community detection problem that the GNN is trying to solve. However, for different kinds of alignment, this might not be the case. And here we are, the formula is not that important, it's a little bit scary, but it just means that there's that the amount of informativeness that the communities are giving to the task also affect how harmful the rewiring will be. And we try this not only for in this theory, but we also support it with some experiments on SBMs. So we test a GCN, and we see that this alignment, or the way that we define the task on top of the SBM, is indeed very important, aligning with this third theorem that I've talked about before. And so we also see, or this is because we are just defining the features on top of the labels, of the community labels, we see that by modifying the SPM, so by modifying the community strength, we are also changing the number of same labeled edges. That is the number of edges that connect nodes with the same label. And because this changes, this is reducing homophily. And in the case of SBMs, this is very important for the task, and so this is detrimental. Now, we also see this not only on SBMs, but also we see this in other datasets, especially homophilic, which are the ones that have more community structure, and, well, usually, not necessarily, but in the cases that we have here, yes. And homophilic graphs are the ones that have edges connecting nodes with the same label, or mostly. And so these are more similar to these SBMs in this setting. And we can see here, for instance, in these lower graphs or lower plots, that by adding more edges to maximize the spectral gap, then we are decreasing the text accuracy, but we are also destroying the community structure and its alignment with the task. So the effect, or the good effects that improving connectivity might have quickly degrade, or even are not there in homophilic graphs. But this is not necessarily because they're homophilic, but maybe, and this is more important, because the community is destroyed. Now, the main theoretical insights here that we can get is that that the information, or that the informativeness of the graph, that of the communities with respect to the task is very important. And so by destroying it, then, well, yeah, you don't want to destroy it. So what can we do in order to challenge, or to do some kind of graph rewiring that takes into account both things at the same time? So we want to somehow choose whether to increase or decrease the communities, but we also want to choose to increase the connectivity, or the information flow between parts of the graph that might not be from the same kind of community. So I think that we could do is to just calculate the alignment in some sense and choose to whether to increase or decrease communities. I mean, this is not necessarily what we end up doing, because calculating the graph task alignment is very generic. It's like how much informative the labels are with respect. We don't really have the task labels here. We don't really know how they will affect. So now we're going to study some specific methods and that tackle communities. So taking into account just the community structure. We can also take into account just the task, and we can somehow combine them together. And we will see which of the datasets behave well for one thing or another. And this is a case study of all of these different methods. Now I'm going to explain the methods. So the first
Celia, sorry for interrupting you. We are running out of time. Can you wrap up in a few minutes?
Okay, awesome. Yes.
Sorry.
Yeah, of course. Well, I've mainly described the methods already. So the first one would be to increase or decrease the community structure by detecting it and then choosing what to do. So yeah, adding edges, intra-community edges or inter-community edges, depending on what we want. So these are these kind of methods. The second one is focusing on the task. And because we don't have the labels here, I'm just focusing on the features and how to maintain this same feature denoising to not reduce, at least in the homophilic cases, to not destroy the community structure, destroy the edges that are homophilic in a sense, right? And so we are going to choose the edges that are maximizing the feature similarity. So the ones that are very similar will be added, and the ones that are very different will be deleted. Awesome. And now how to combine them? So we will do both things at the same time. So we will check these different edge areas, inter-community, intra-community, and we will choose whether to add or delete proportionally. In a sense, we are taking the spirit of doing a local kind of a local kind of rewiring by doing a focused feature similarity maximization. I hope this was clear, but I mean, it doesn't really matter how we exactly we define them. It's more about whether to take into account the structure, whether to take into account the features, or to somehow combine them both. And now the comparison between the methods is perhaps very interesting because not a single method works for all of the things. So this is, as we've said before, it really depends on the task, and we can see here that the three first columns correspond to these homophilic datasets, and the other five correspond to heterophilic ones, which are the ones that are connected, that have nodes connecting that are with different labels. And so, first of all, the spectral gap maximization is working well, but it's not the best one, and we can also see that it is still better than the ones that are just about the communities. So the one that is the 4 comma ones are just not performing that well, but this is to be expected really, because you really don't know which ones you're taking or not taking. And so the important part here is how the homophilic and the heterophilic ones work differently. So the method that just attacks feature similarity on its own without taking into account how the graph is structured at all performs the best for homophilic graphs. And this is, of course, to be expected, but also it's precisely what we have been doing our theory on. And so for the combination of the community structure and the feature similarity is the one that usually works better for the heterophilic ones instead. And I have to say here that the homophilic graphs, the heterophilic graphs might not have a specific community structure. So it's not necessary that they have a full community structure. So increasing it or decreasing it might even not be really informative, but it is still good to separate the graph rewiring across different parts of the graph. And this is why it's working better. And finally, and maybe a callback to the other work that I've talked about, is that edge deletions are usually more effective in all of the cases. So as a conclusion, and again, one has to consider why we are rewiring and where the gains really come from, whether from the computational challenges or from the data that we are changing. We are literally changing the data, and so we have to avoid some kind of catastrophes that happen with graph rewiring. Thank you so much.
Thank you, Celia. Thank you. So all the questions and discussion are deferred to breakout rooms.
Awesome.
Thank you for the talk. Now we can